Swayam Prabha. Digital India. Educated India.
So good morning. Okay, so today we go to another area that is a little bit of, I used to say, a kind of unconventional corrosion issue. That is the corrosion electronics. And maybe many years back, people were not thinking that this problem is existing. And then that was because most of the people, most of the people dealing with electronics was the electrical and electronics people. And whenever they see a failure in the electronics or electrical systems, they think that is an electrical failure, and they just either try to solve it by changing the component, or they used to just throw away the part and then they put the new part and like that. So they were not thinking that there is a corrosion component in it, and that they were not understanding. And there are a few other reasons that IIT has become much more prominent over the last few years. But now when they understand that this problem is there, it is becoming more and more. And it is more and more important today, especially when the electronics is used everywhere. And so that way, there are so many companies and other people are worried about this issue and how to solve it. And I'll come to the more details later. So what I'll do is that the first part, I'll give a little bit of glimpse of an overview of kind of materials that are used in electronics. Everything we'll not be able to cover, but just to get an overview of what is important. And then connected to that, what is reliability issues. And when we go to the next part, we will get into a little bit more these failure mechanisms in a little bit more detail, and the mechanisms and things like that, and how we are trying to find the solutions and all those things we will look in the second part. I mentioned that we have a center at DTU, which I established in 2016. And why I established in 2016? Because there were power electronics manufacturers in Denmark, like this company Grundfos. Probably you heard this name. There's a big part in India. They make pumps, very high profile pumps for different sizes, for different applications, and with the attached electronics in it, so to drive the pump. And Danfoss is a power electronics manufacturer. They are making the frequency converters and things like that in relation with the solar energy, wind energy and things like that. So they are also power electronics manufacturers. And there were, at that time also there was Vestas as well, because Vestas also used the electronics in the wind turbine. So they had this issue, and they were, and interestingly in 2016, Danfoss was the only company realized that their failures are due to corrosion. None of the other companies didn't realize that it is due to corrosion. They thought that it's an electrical failure. That's what is happening, and that's the way they categorized. So Danfoss came and asked us that whether we could look into their problem and whether we could work in that area. So that's the reason way I started, when combining different companies and making a consortium out of it, and that's where we started. So then more and more companies started realizing that yes, there is a problem, and then if you start from there, and then you can see that, like of course the Bosch being a automotive electronics manufacturer, they knows that this issue is there, but they were also not knowing so much. And then it slowly it picked up, and now I think everybody has these issues and they're trying to solve it and like that. So we collaborate with many companies all over the world in this, and we do a lot of activities at the center. As I mentioned, that the reason is that electronics is used everywhere today, and that means that all these electronic systems, which contains a lot of materials, so much metals put together, because it's an electrically conducting media, right? If you take the whole electronics components, and electrically conducting tracks, and the electrodes should be made of metallic materials. So which means that it is, we can understand that it's susceptible to corrosion when it is exposed to corrosive conditions. And because the issue is more today, because as I mentioned that it is used everywhere in the world, and so there is very harsh climatic conditions that is getting exposed. In addition to that, over the last 20 years, if you take, this miniaturization and integration is a key things related to the electronics. Think about mobile phone. Like earlier, we had this, there are small Nokia mobile phone, and the functionality of those mobile phones are also were less. Now we have slightly bigger than that flat one, but the functionality is so much in the today's mobile phone. That means that so many things are integrated into that. If you take the opener and see the printed circuit board, so many things are integrated there, and that means that in order to integrate that, everything has to be miniaturized. So all these component sizes have come down so much, and also the PCBs have become multi-layers, which I will come later. Not one layer, but multi-layer PCB. And so that makes, you can imagine, that is, when the component is smaller, when the water droplet forms, it is much more easy to connect, right, between the points. It's as simple as that. And the component size is today come down to the level that when you have the condensing droplet, and it is within the size of the condensing droplet. I'll show you that bit later with the video and like that. So that way, miniaturization is always going against the corrosion things. And in addition to that, if you take this kind of modules, for example, this is, we call it as IGBT, that is integrated gate bipolar transistor, which is a power converter. This one, which has to be part of the wind turbine and things like that. And so this one has to take very high voltage. Probably the voltage in such systems will be 1000 volt. And there are many metallic joints. This brown color what you see is copper pads. And then on the copper pads, I don't know whether you can see some wires. There is a small thin wires connected to these silver thing what you see is a semiconductor. And to semiconductor you have joined this thin wire. So there is very thin joints. And all these has to carry power. And then you think that, and then this entire IGBT is supported with a silicon gel as a protective measure. So there's a thick layer of silicon gel. But humidity will go through silicon gel. So humidity will go through the silicon gel, and when it reaches the silicon gel, this PCB interface, like the coating, slowly it start failing. And once start failing, you have a very high voltage across these different points, and then you have a big problem. Some of the wind turbine caught fire because of such kind of component, which is as a corrosion problem. And then there was an electric short. That electric short created the fire, and that is just one component, entire wind turbine, yes, caught fire, like that. So, so this miniaturization integration is one of the key things, which also good to remind ourselves is Moore's law. Moore, many years back, he suggested that like this integration and things like that in the electronics is going to come more and more. And he suggested that the number of transistors in integrated circuits will double every 2 years. That's what he suggested, his theory was, the way the technology is going. That is still true if you look at it. Still true that Moore's law is true. Probably it is getting more than double, but maybe 3 times. It's becoming like that. So that is the way it is, and that is really goes against the corrosion problem. Everything what we are talking about is, if you take the printed circuit board as an example, you have many of these components which has a 2 part, you can see that. So this is a resistor, and that means that when you have 2 parts, one part is positively biased, other part is negatively biased. What means that since being a resistor, across this resistor probably you can have 10 volts or 20 volts, 48 volts. Depending on the resistor, you can have 1000 volts even, depending on the resistor across this. Similarly, if you take this is a diode, and again you can have a potential difference between these two and potential difference between these two. So it's like a electrolytic system, and so that's the case with everywhere. And then you can imagine that when the water film is forming, so a thin water film is connecting between these points, automatically that will trigger an electrochemical cell, right? It will trigger an electrochemical cell, and you have the positively biased electrode, and that become anode and cathode, and then you have the whole electrochemical process. It's as simple as that. The only thing is that added to this water film, you can also have the gases that is dissolving into the water film, because it's a very little thin layer water film, and that will change the chemistry, and that way also we can add additional problems with this. Aerosols or things like that is less of a problem in the electronics, because most of the electronics is packaged. So when they package, they make sure that the packaging is tight enough so that only humidity will go in and gases can go in, not the particles. So that way the aerosols are not that much of a big problem for the electronics. And that will cause many failure modes. And although some failure modes are more important than the other one, but just in general, it causes many failure modes. So this is a typical, we call it as creep corrosion. So that means that corrosion has occurred on copper part, and then the corrosion product is spreading. That's the reason that is called creeping. So it's creeping across the surface. More of a cosmetic issue. It may not create a failure immediately. This is another one when you have the silver on the surface. Silver dendrite is forming. This dendrite is silver sulfide. So it's in a H2S condition or SO2 condition. Silver will react and form this kind of dendrite formation. Again, dendrite formation itself is not a problem, but when the dendrite is forming, actually the thickness of the silver line is coming down because of corrosion. Silver is converted into silver sulfide. And if the silver line has to carry, say, 100 amperes of current, as the thickness is reducing, its current capacity will come down. Right? Current capacity depends on the thickness of the line. So the current capacity will come down, and so that means the resistance of this line will increase, and that will ultimately cause problem. There were many metro trains in Delhi that was failed because of this problem. And because the Delhi metro trains were actually supplied by Bombardier, which is the big part of this Bombardier train manufacturers in Europe. And actually we were working in that issue together with them, and that was failed because of this issue. This is inside integrated circuit, because inside the integrated circuit there is a gold and aluminum coupling. Corrosion point of view, we really laugh at it, right? Having a gold and aluminum couple, anybody will put it. But integrated circuits, whole integrated circuits contains this micro gold and aluminum joints, and there are several reasons for that why they use it, and that will fail because of corrosion. This is another type of failure which also you show in my front slide, that is called electrochemical migration. That means that the metal is, when you have this anode and cathode, from the anode metal will dissolve, and because of the high bias, that metal will go and deposit on the cathode, and then it will make a growth like a dendrite, and then you get an electric short like that. So that's a very serious failure, because that will, within a short time, it can create an electric short, and then you have functionality issues. A similar thing could happen inside the PCB, because if it's a multi-layer PCB, it can happen inside the PCB as well. That is what is shown here. And all kinds of components are involved in this. That is integrated circuit. Inside the integrated circuits, you have a problem like this. Outside the integrated circuit, between the legs, you can have a problem like this. You can have the problem on here. You can have the problem on this capacitor, or you can have the problem like on these IGBTs, like what you have shown here like that. So it is just to give a glimpse of like how different components get involved in this. So this is showing that it is just to show you that that's the most important material. What you see it on the printed circuit board. Like this printed circuit board. So what they do is basically first they make this printed circuit board with all these tracks and all these places where this component has to be put in, and that's what is called the PCB layout. And the PCB layout, so that means that all these conduction lines and this pad here on the PCB can be of different surface finish. It can be surface finish with gold, or it can be silver or copper surface finish. Copper is very little used. Base layer on the PCB is always copper, but that copper is covered with something else on the top. So usually tin is the one mostly used, because tin is when you put the component on the top of this soldering is done here like this, the soldering process, Soldering process also use the tin alloys because tin is a low melting alloy. And since the tin is used for the soldering process, on the PCB surface as well, all these pads, they cover with tin. So initially there is copper, and then that they cover with the tin because then it is very easy for the soldering process. So most of the industrial PCBs, the main material what you see on the surface of the PCB is tin or tin alloy. That's what you see. Because all these component legs are coated with the tin, and these pads are made of tin or tin alloys. So that's what you see. But if you look at the PCBs that is used in the mobile phone, you will see that the pads on the PCB is made of gold. All these are still tin, but the pad on the PCB is made of gold, and like that. So it is depending on, there are many things to consider there. So that's the reason. But let us take the industrial PCB where most of the material is tin. And if you look at this chip capacitor, again this electrode surface is tin, this electrode surface is tin. It's the same here. Here these legs, although the inside material is different, but outside you have the tin coating. So the tin is the surface that is exposed as well. Inside will come later. Inside you have gold wire and all those things in the integrated circuits. We'll see that later. So that is just to show you that what is the prominent material which you see on the printed circuit board. I think I mentioned here that is most of the this one. But as I mentioned that all these failure modes are created irrespective of whether it is a high power or low power system or but everything involved. That's our role to play. The materials and electrochemical people or corrosion people, our role in this one is that because all the mechanism here is electrochemical mechanisms, and if you can understand why these electrochemical failures are happening, what is the material issue related to that, environmental issue related to that, we can try to solve it. So you can understand that this is a multidisciplinary area. There is materials and corrosion people like us should be involved, and electronics and other people, we call it as power electronics people, researchers, they also should be involved. So power electronics people also, some of them will work with these humidity issues, but they don't understand the mechanisms, electrochemical mechanisms. They don't understand the material contribution. They don't understand the process contribution and things like that. So mostly they work with, electronics thinking. They work only with, they take this component and do multiple testing, and then they get the failure time. They plot the failure time, and then they calculate the average time to failure from that, and a little bit of prediction and things like that. This is what they do. So they don't remove the fundamental mechanisms. And this is also like we could contribute a lot because we got into this area in 2016 very early because of this Danish company's request, and that is then we increase these collaborations and things like that. We've created a certain unique expertise with our corrosion and material expertise, which other people are not having it, the power electronics people. So this is a good thing with us. And that's the only way we can solve also the problem, which I'll come probably in some other slides. It's coming. Yeah, because I think I want you to get this clear idea that if you look at any product, if you look at it, like the overall system life of a product and failure rate, if you look at it, this is a typical bathtub curve everybody use when they make a system. And so if you look at the system lifetime, so you have the system lifetime starting from 0, and it is the end of the life here. And we call it as, normally you see a typical this bathtub curve. That's what you see. So when you make a system, sometimes a system will show some initial failures, early failures. These early failures are due to, we call it as infant mortality. That is because the system is defective. When they design the system itself, there is some defect. And because of that, it is failing. These early failures, they will remove it immediately because then when the product is made, immediately they understood that system has some weakness and they rectify that, and that means that this early failures is immediately reduced. So this they don't have to worry because this is the system defect when they designed it, and they remove it before they start putting it in the market. Then the system is started using it. What people expect is only the wear out failures. That means that system will get aged up to an extent, especially in the electronic systems. And when it comes to say 10 years or 15 years, then slowly the system will start failing it. Why it is start failing it? Because one of the other biggest problem in the electronics is thermomechanical fatigue. That's coming because all these, if you look at this, all these joints here, this solder joints, this solder joint is having fatigue because when the PCB is working, it is increasing the temperature, say to 80 degrees centigrade or 100 degrees centigrade. When PCB is not working, it's cooling down, so there is a thermomechanical stress because of the difference in the thermal expansion coefficient. In addition to that, depending on if the PCB is used in the car, this is vibrating, right? So both together will create a thermomechanical related failures in these PCBs. That's one of the key failure mode people see in the electronics, and this thermomechanical failure is a wear out failure because this takes time to happen and this can be predicted, right? So you can do many experiments in the lab and you can make a model for the thermomechanical fatigue, and almost we can predict that, okay, this joint can work until 10 years like that. So this is what they do, electronics people will do, power electronics people do, and they know that with models they have, and then with that models they predict it will take at least 15 years for these things to happen like that. Do you think that our corrosion failure will fit into that? This is exactly the issue. Corrosion failure will not fit into that because corrosion failure is not an aging failure. Corrosion failure will happen when there is a conducive condition is forming on the PCB surface. There is a condensation on the PCB surface. Transition to the failure is very, very fast. Only thing is that you need to have the condensation that is happening on the PCB surface, and then probably from this point to this point it will take only 15 minutes or 30 minutes. That's all the time period. So as long as 30 minutes you can have the condensation existing on a PCB surface, you can get failures. On the other hand, here we are expecting around 15 years. This is the issue. And this is one of the issue also. It's very difficult for the power electronics people to understand because power electronics people or electronics people always used to the model and things like that, and lifetime calculations and everything. They think that it fit into the this aging mechanism. I try to tell them every meeting when we have together, I try to tell them that don't think that corrosion will fit into that. Corrosion is not a aging type of failure. It's very, very difficult for them to understand. They don't understand any type of failure mechanisms in this world exists which will not fit into aging mechanism. This is what they say, think. So what I mean is that that means that if 30 minutes period, you can get the condensation on the PCB, and that is enough to get the failure. So that means that we call it as in electronics term, we call it as it is not a reliability issue, it's a robustness issue. The system is not robust to withstand that condensation for 30 minutes. Reliability means the system has to work reliably for 15 years. That is reliability. Robustness means if you start increasing the stress on a component, what level of stress it can withstand without failure, and that is what is robustness. So this is a robustness issue. As long as the condensation is, so the question that comes back is that is like when you have this 30 minutes condensation, how we can make the system robust in such a way that the 30 minutes condensation, it will not lead to such failure. That's the question comes, right? So it's a robustness issue rather than the reliability issue. When I also say that this is happening with 30 minutes, that's why I put also this one here, this climate profile here, because this is this corrosion is an atmospheric corrosion type, right? It's not like our other type of corrosion where you have it's immersed in water. It's like atmospheric corrosion because of the atmospheric change in the climate. Because of that, a condensation is forming. Like yesterday we were discussing about a car. In the morning, what you see, the condensation is that is happening. So this, if you look at this climate profile here, you have the temperature, that's red one. You have the relative humidity, that's the blue one. And then you have the dew point temperature, that is the green one. Right? And when you get a condensation, what is the condensation means? Any surface, when you will get condensation? Yeah, on the surface is less. And so we say that if you have the humidity, if you have a humidity level of 90% in the air, and the temperature in the air is 25 degrees centigrade, you need to reduce the temperature to some degree, then you get a condensation, right? So that temperature which you need to reduce, that is what is called dew point. So say that 90% relative humidity outside, temperature is 25 degrees centigrade, the dew point is 23. So that means at 23 degrees centigrade, if something you cool down to 23, then you start getting the condensation. That's what it means. Or we can say the condensation chances are more if the dew point temperature is close to the ambient temperature. So if you look at this profile, you can see that this is a period at which this dew point temperature is close to the temperature. So in this day profile, starting from 12 o'clock to 12 o'clock in the night, means midnight to midnight, if you take, this is the area, there is around 2 hours period in the early morning, there this dew point and this temperature is close. That's the time you have a chance to get condensation in the PCB if the electronic system is off. Like I was saying yesterday, the solar energy is not producing in the evening and the night they will shut off. And that's a period they can get this 2 hours period. If that 2 hours period here, maybe within that 2 hours only half an hour is critical. If that half an hour, either if you can avoid forming the condensation here, or even if the condensation is forming, you can avoid the failure, then you get the robustness, right? Then it add up. And then the system will work like that for every day you may get condensation, but it not fail. System will work like that for 10 years or 20 years period like that. So that's what I'm saying, that how can you increase the robustness? That is exactly the kind of things which the materials and corrosion people do. How the system can be made more robust. There are also things are changing in the electronics world. That is, if you look at like, earlier things are, electronics probably work with some systems with 2 volts. Maybe it was going up to 48 volts or 100 volts. But now that's not the case because the things are changing, as I mentioned earlier as well. That is, all electronic systems are going up to 1000 volts and 1000 volts on the PCB surface like this. So you have a lot of electrochemical potential for the corrosion to happen. And another scenario which is changing is that in addition to the humidity, you also have the synergetic effect of gases like H2S, SO2 and all those things that will change the failure modes. And so that's what I'm saying. So that means that as the system is changing in this direction and in this direction, we are expecting that this is a new thing. Actually, that's what is happening. We are expecting that is modification of the failure mechanisms and inducing a new failure modes. That's what we'll see. Gaseous condition and things like that. And that's also the role which for us to play as well. Because if you look at the power electronics group, again, as I mentioned, that what they do is, they do this things called high voltage, humidity, temperature, cyclic testing and things like that. They take a component and do that kind of testing. They get the failure data and they plot it, make some models out of that which will not obey the mechanism and things like that. So this is the issue. And that is what we are trying to fill up. That is like people like our group, we know the materials and corrosion and we also learn the electrical and electronic aspects and we can bridge these two together. They do the testing of the actual component because this actual component testing is not that easy. Because this has to be tested with the 1000 volts and very high current levels. And I cannot test in my lab that because there is a lot of safety issue related to that. But they can do that testing. But they don't understand the mechanism. So because they don't go into the materials, failure analysis in detail and things like that. But that is where we enter so that we can bridge both together. Today what we do is in our lab, we can do testing up to 100 volts. That itself is a quite high voltage for the electrochemical point of view. And we can also do certain level of gaseous conditions, but not to the level of multi-gas testing. We can do certain level of gases and we can do 100 volts. And in the electrochemistry, this 100 volts is not bad because the reason is that when you have such a thin film of water, this is what we say, which we also have to prove and we also have to do a lot of things to make sure that this is the case. When you have thin film of water, there's no point in increasing the voltage. Because even if you increase the voltage, you come to the stage that you cannot pass more current through the solution, right? Yesterday we were discussing, I don't know which group we were discussing, by drawing this polarization curve. When you are keep increasing the potential, depending on the conductivity of the solution, at one point you start seeing this resistance limit. So you cannot pass more current. So we do the modeling, electrochemical modeling. Electrochemical modeling also shows that there is a saturation of current. Like you can think about that, if you have a copper wire of certain thickness, what happens if you keep increasing the current? At one current level, the copper wire will burn because it's going to take more current. In a similar way, you cannot pass above a level the current through the water film, and you maybe because of the resistance, it get heated up and the water film will evaporate. That's all. So there's no point. Actually, there's no point in increasing the voltage, but we need to prove that the increase in voltage will not create any new mechanism. So that's what we can do 100 volts, but we want to go into the much higher voltage. And this is a case with everywhere, because as I mentioned earlier that you need to DC to AC conversion you need to do, and then some places you need to do AC to DC conversion, and again like that reverse. And so everywhere you need to use this kind of systems, and everywhere you have such kind of electronic modules inside, and that is getting exposed to this kind of conditions. So it is keep increasing. And to show you that why this is important, yesterday I was mentioning that this, when we are measuring that wind turbine thing, that is, this statistics shows that in the Germany, Denmark and Sweden, the electronic sub-assemblies fail fast compared to the other things. So the mean time to failure for the electronic sub-assemblies is around 30,000 compared to that of the gearbox, which is around 87,000 hours. So that is one thing which I am showing, that is the importance of the electronics, why that is need to be taken care of. I think this we can leave it. But then to show you a little bit addition to that, the Fraunhofer Institute in Germany has done a very nice investigations all over the world, but I am showing here the Indian wind turbine fleet and the Scandinavian wind turbine fleet. Scandinavian means it is the combination of Denmark, Sweden, Norway and Finland. So this is what we call it the Scandinavian part. And you can see that if you look at this failure statistics, the failure per wind turbine, there is failure occurs all over the year, but you can see that the number of failures is more during this period, and this is a period where you have a higher humidity condition as well. So you can see the relative humidity is also higher during that period. That is the period you get a much higher amount of failure. But that doesn't mean that it is due to the corrosion, but they did the analysis. So they collected all these failures and then analyzed them, can clearly see that many of them are due to the corrosion failure. So there's a clear indication that the climatic conditions, how the climatic condition is changing, and that is leading to the more electronic failure due to corrosion. So that's one thing. And the similar effect you can see slightly shifted by the month, you can see in the Scandinavian fleet as well. And Scandinavian fleet, you can also see that there is more failures here as well. That's because Scandinavia always there is a lot of temperature is lower, and in the winter time again you can have a lot of condensation and things like that. So that's the reason that all the time there is a failure there. And similar thing you can see that the solar energy, and solar energy when you produce, you also need to have these electronics attached to that as a conversion system. And again you can see that there is, again they did the study the same, Fraunhofer Institute. You can see this humidity level, and you can see the share of the total inverter failure, and you can see that correlations. And again they analyzed many of them, and they can see that it is really due to the corrosion failure. So in this particular case, you see there was a corrosion between these two components got connected. So there was a water film. So these two components got connected, and maybe this was positive terminal, and this was negative terminal. So the metal has dissolved and deposited between these two and made an electric short in this particular case. I'll come to that, the mechanism of this one later, and that's what has happened. So that's what you see in that case. So there's a real correlation. So that's the reason that everybody is worried about humidity related failure. So same story, people will say train manufacturers like Siemens and people like that or Bombardier making the train manufacturers, they tell the same story, that they are more worried about the humidity rather than any other failure modes. And this is also a chance for our people like us doing the corrosion and materials work. So if you look at the corrosion possibilities on a printed circuit board, and especially metals are the most of the culprit here, because metal is the one which is causing the electrochemical failures, right? Although polymer can also contribute by degassing. I'll show you some examples of polymer degassing, and that polymer degassing and causing the corrosion on the metals. There are cases like that. So that is supporting the corrosion, but otherwise metals are the one which is causing the key corrosion problem. So based on what I told before, if you just look at like how can we generalize the corrosion problem on the PCB surface? You can generalize the corrosion problem in two categories. One is the corrosion due to the gases, and we will see that later. But corrosion due to the gases with maybe there is moisture or without moisture as well. It can be like that. Other one is electrochemical corrosion, direct electrochemical corrosion, because there is a wet media like a thin film that is forming on the PCB surface, and when that wet media going on the PCB surface, you can have two types of corrosion problem. One is the galvanic type of corrosion problem. There are many multi-material combinations on this. So if you take this is a gold pad, you see it on our mobile phone, not new mobile phone, but earlier mobile phone had a key, right? You press the key. In the old mobile phone, I don't know whether any of you have seen that in your age, but there is, you press the key, and below the key, you have this kind of pads. This is made of gold on the top. Below the gold, anybody knows what you see below the gold? So below this gold, there is electroless nickel, and below electroless nickel, there is copper. So there is a base copper on this one. On the top of the copper, they put electroless nickel. Then on the top of that, in order to get a good electrical contact, they put gold, because gold is a material which can give very good electrical contact, right? Because gold is a noble metal, it's not having any oxide. So for all electrical contact purposes, they use gold on the top. And this gold layer is very, very thin, because gold is very costly, so they don't want to put too much gold. So this gold layer here is probably 100 nanometer thick, 100 nanometer thick. So that means that inherently, if you know the electroplating, you know that that gold layer will be very porous. So that means that electroless nickel will be exposed. So such kind of places you can have the galvanic corrosion problem. But this galvanic corrosion problem is less worrying, except in some cases, because still the system can work for some time without any problem. The other one is, as I mentioned, that is the electrolytic type of problem, because already there is a bias, and when the water film is connecting, you get this kind of electrolytic type of corrosion problem, and that is much more worrying, and that can lead to many failure modes. So just to elaborate a little bit on that, so this galvanic corrosion problem is gold. So you have the porous gold layer, you have electroless nickel below that, and then the copper. And then if the gold layer is porous, when the water film is forming, it get connected, and then you have this electroless nickel will corrode and gold will peel off, and then you have all electrical connection problem. Why they put this electroless nickel below the gold? What is the reason that why can't they put gold directly on copper? Electroless nickel is also right. Actually, that way electroless nickel is bad, because electroless nickel is below copper, right? We call here different, 24 karat gold, 20 karat gold, right? What it means? Amount of copper. So that means that the copper is very soluble in gold. So if they put gold directly on the copper, there will be interdiffusion between copper and gold, and that means that so many different types of intermetallic particles and phases are going to form between gold and copper. So the diffusion barrier, this nickel will act as a diffusion barrier between the copper and gold. So that's the reason that anywhere they use electronics in gold in electronics, you need to have if it is going to be on copper, you need to have a barrier layer in between, diffusion barrier layer, that is the electroless nickel. So that's the reason that they use electroless nickel. So that's a typical example of galvanic corrosion. I'll show you more later. So that's the reason that people, I just showed few values. That's the reason that even people have made a galvanic series for the electronics work. Galvanic series means, you see here, what is this? It is called flux contaminated solution. Because for the electronics, it's a sodium chloride and things like that is not the important one. When they manufacture this PCB, in order to do the salting process and things like that, they need to use a chemical flux. That chemical flux will have some residues which is sitting on the PCB surface. That is a contamination, that's the residue, not the sodium chloride or anything. And that's the reason that they do this experiment and make this electrochemical series or galvanic series in the flux contaminated solution. There are typical sort of flux systems and do that. And normally this solder flush system contains not chloride, but it contains weak organic acid. Like not acetic acid and like that, but there are weak organic acid like malic acid, glutaric acid, and those are the component in this kind of flush systems. So that's the important environment for electronics. Another one is, as I told, that which is connecting between the points because of the bias, opposite bias, and then that way it is causing this corrosion problem in electrolytic. We will see that in detail later. That's another issue. I told the transient effect, which means that it will not happen all the time, it will happen only sometime. Now there are certain things also you need to understand about this water film formation. It's a very thin layer of water film, probably maximum is few micrometer, but it can also be nanometer scale, this water film thickness, and that means that its conductivity is also limited. That is one thing. Second thing is, always you have a high potential difference between these two. Minimum 2 volts we can take, and that means that enough for the hydrolysis of water. So hydrolysis of water is a side reaction always when this is happening, when this is forming both at the anode and cathode, and that has repercussions. Because when you have a hydrolysis of water producing so much hydrolysis of water on both electrodes, and that means that one side of the electrode you reduce the pH, and other side of the electrode you increase the pH. You have a very sharp change in the local pH on both sides of the electrode because of the hydrolysis of water. And you will see that later, that is when you have an experiment, at least 50% of the current is used for hydrolysis of the water, and 50% of the current is only used for doing the metal dissolution. So that means that there is a lot of hydrolysis of water which produce a lot of this pH change. There is a field assisted this movement of ions and deposition. So that means that there is another thing which you don't see in the case of, for example, when you are doing an experiment in the electrochemistry lab with 3 electrode system, your working electrode is there, your counter electrode is quite far away in this case. So counter electrode is the one which is supplying the current, right? To adjust the potential of the working electrode, counter electrode is the one which is acting as a mirror to the working electrodes. This is quite far away. So the field between this one is not that high. But here you have this high voltage, this is very short distance. So you have a very high electric field acting through the solution. So whatever metal is dissolved here, metal ion, it can be pulled to the cathode. And it can be pulled to the cathode, and then it can deposit there, which we will see later, deposit there, and that way there is a field assisted movement of ion and deposition, and that's another thing which is important to think about in this case. What it can lead to, because I'll show you, I will this one take again next time, but I want to show you that you get a short circuit. So basically what happens is, this last point what I mentioned, you have the water film, you have the metal dissolution, field assisted movement and ion deposition. So metal is dissolved here because of the field, that ion is pulled to the cathode, and tin is a very easy metal to deposit. This is another problem in the electronics. Most of the metals that you see on the electronic surface is very easily depositable metal according to the electrochemical series, like a tin, copper, and all these are easy to deposit. It's come and deposit here. Since it's a field assisted deposition, it will not deposit uniformly. Instead of that, it will deposit at some point where the field is high, and it grows like this in the form of a dendrite, and then you get an electric short. So once it creates an electric short, now this is a metal wire, like a metal wire, right? This electric short. That metal wire will carry, a lot of current will pass through the metal wire. It's like a fuse wire. And because of that, this wire will burn. And then if the water is condensing still, it will happen again, it will burn, it will happen again, it will burn. What is the consequence of that? As each time, if this is happening on a PCB surface, each time it burns, it creates a small spark depending on the voltage. That small spark will burn this polymer, because this base PCB is green color stuff, is a polymer, it's a glass epoxy composite. It will burn little bit, and this will create a little bit of carbon, very little carbon. This carbon will start depositing here, and carbon is this deposited carbon is a very high resistor. Slowly what will happen is, you form a very high resistance between two conduction lines because it's carbon deposition. It becomes red hot and the PCB catch fire. So that's the end result. Again, coming to that wind turbine failures and automotive failures, and then this is what happens. So it starts with just a water film formation, humidity effects, and with a fire. So Bosch also put a name for this failure mechanism. It is called a thermal event caused by non-thermal event or something like that. And they put also a name for this because it starts with a water film formation. It's nothing to do with a fire, but it ends up in fire. And there are so many German automotive companies, they lost so many cars while transporting just because of this issue. So that is what I'm saying. It's a serious issue, although it's not just a simple failure that results in, but in some cases it can also lead to such kind of dangerous things. Now, anyway, like when you take an electrolyte, you need some conductivity, right, for the electrolyte. So the pure water film, condensed water film is more of a resistor, right? What is the resistance of a water, pure water? 10 to the power of 8 ohm, right? Around that. And so you need to have some conductivity of the water film, and there it comes to the importance of these ionic residues which is on the printed circuit board surface, which comes from the manufacturing. When the PCB is manufactured, as I mentioned, that they use a flush systems to solder. This flush system will have some residues on the surface, and the residue will be dissolved into the water film, and that is what is actually causing this increase in the conductivity. So if you put together all these, what I can say that is, like, there are metals and alloys on the PCB surface which can easily get connected. Already there is a bias to create the electrochemical cell. So you don't need a difference in the electrochemical potential because this bias potential is enough to create a difference. Humidity is there to form the water film, and then there is this contamination which like these tiny levels of process related contamination which is existing on the PCB surface, and that will dissolve into the water film, and that provide the conductivity for the water film. It's a very, very tiny levels of contamination. So that's the reason that the PCB cleanness is a very important factor. You can see that when they manufacture the ICs, it run in a clean room, and the reason is that it is like this, because when you take integrated circuit, this contamination is much more important, because here we are talking about at least a few hundred micrometer of distance, and in the case of ICs, some distance are fraction of a micrometer, nanometer scale difference there. So there this contamination becomes much more important. That's the reason that is they make it in the clean room and things like that. Also, of course, they want to avoid the contamination in semiconductor as well. And so that explains. So at the end, that explains that how the combination of factors which is important for the corrosion is coexisting on the PCB surface. I think this one I will stop here. Yes, maybe this one as well. Just to show the gaseous condition also can cause a problem, and especially if there is a silver. Silver is one of the most important thing in this case, because sometimes the PCBs are made like this. You don't see the green color here, you see this blue color here, and maybe even you don't see blue color sometimes, you see the white color. These PCBs are made of ceramic. It's not like a normal PCBs where you have green color, which is a polymerizer base. Why they make this ceramic they use instead of polymer? Yes, this is a power PCBs, so it can take more temperature. So when the PCB is working, it generates a lot of temperature, which is the polymer PCB cannot take. Polymer becomes soft. So that's the reason that they use ceramic. But when they use ceramic as a base, they cannot use copper lines. Copper is, in the normal PCB, the conduction lines are initially made of copper, then they put other metal on the top. Here they cannot do that. They need to use the silver lines. So silver, this is a 3D printing actually. This is equivalent to 3D printing. So all these conduction lines are printed on the top of that, and then they fire it like using a silver ink. So since there is silver, silver is very susceptible to H2S and SO2 gas. And then slowly in the H2S condition, these silver lines will corrode. That's why this black color which is forming, that is silver sulfide, and all these dendrite that are forming, that's also silver sulfide. But what is the problem? When these lines are converted to black to silver sulfide, you think that you have a thickness of this much for the silver. Now from the top, the part is converted to silver sulfide. Silver sulfide is not conducting. So that means the actual thickness of the silver line is reduced, and that means that that silver line cannot take the electrical current, and then you have a problem here. Many of the metros in the, as I mentioned earlier, in the Delhi had the main problem was related to this. Probably the air had H2S and SO2, and so then these metros were failing. All these power components were failing because of the same problem. Copper, they cannot put the copper lines like this by printing. So that's the thing, that silver is very easy to print like this and make these connections, but they cannot do that with copper. It's a printing issue, and they have to do it on the ceramic board and things like that. Copper also, even if you can put copper, that will not solve the problem, because copper is also very susceptible to sulfur condition. Copper can easily react with the sulfur. When we think about this last slide, then we go to the second part. When you think about I was talking about inside part. When we think about the corrosion protection of an electronic systems, you need to think it in a holistic manner with an integrated view. Integrated view, what I mean is that you can protect the electronics in two ways. One is, do not worry about this system at all. As long as you can, if you can make this package totally hermetically sealed, right? If you do an hermetic sealing, nothing will go in. So that way they can totally protect by an hermetical sealing. But it's not a viable solution, because hermetical sealing is very expensive. Not only that, they cannot do that because whenever you have an electronic, at least some cables, some wires has to come out. So hermetical sealing is not possible. So what I want to say is that this packaging is also important. So you can also think that if you make this one better, it's good, it can withstand more humidity, but you can also think that you are designing this one in a nice way, so that even if there is a fluctuation in the humidity outside, this will be damping that, so you will not be able to see that fluctuation inside. So the packaging is also an important thing. So we work with both. We work with this one, understanding this and how we can increase the robustness of this part. We also work with the packaging, so that how we can make a good packaging design, so that we can reduce the effect of this climate changes, whatever is happening outside to inside. So we create a lot of fluid flow models, so that we can actually put any geometry of such kind of things with any type of opening and things like that, and then we can model it with our experimentally verified models, like if you have that packaging, what will be the humidity built up inside with a certain conditions and things. I'll show you a little bit on that at the end. So the point I want to say is both are important. We call it as intrinsic way of increasing the robustness, that is making the inherently these components much more robust. Other one we call it as extrinsic, which means that we are putting a barrier like a coating. Only thing is, it can be the coating or it can be the packaging, and that we are reducing putting a barrier to the humidity which is coming to the PCB surface. Both are important. When the PCB is working, the problems are not there. The problem comes when when the electronic system is off. That time the condensation has formed on the PCB. Then the morning they come and switch on. Probably that condensation exists for 30 minutes or 1 hour. That's the time the problem comes. Yes, that's why there are coatings which it's called conformal coatings for the PCB surface, because it also has to conform to the, you cannot get the normal paint, because it has to conform to these contours of the PCB. So those coatings are there, and those coatings are actually made within such a way that it also has enough heat dissipation. But it is very thin. It is maximum thickness of the coating on the PCB is 150 micrometer. So it's not like paint where you have 600 micrometer and things like that. So it's very thin, but it has enough heat conductivity for that. But again, you cannot say that same thing can be applied everywhere. There are places where even that 100 the 150 micrometer thickness coating you cannot apply, because it is that PCB is generate a lot of heat. So the heat dissipation is more important there, so probably they will not be able to use a coating. So that rule is also universally you can apply. And I also wrote a book actually. Yeah, probably this I already told. This multi-material combination is there. Miniaturization is another thing. Both galvanic and electrolytic corrosion is possible. Thin electrolyte layers, that's an important thing. And electrolytic type of corrosion is more important in this case. And electrochemically, when you look at, there is high voltage. Bias level is enough for this electrolysis of the water and metal ion reduction. Contribution of ocean reduction to the cathode reaction negligible. That's why normally when you have a thin film, thin water film, always we talk about increasing the ocean concentration, right? We don't worry about that here, because ocean is not an important thing here, because we have enough voltage to split the water. So the main cathode reaction is splitting the water and the deposition of the metal ions. And conductivity is created by these residues on the board, as I mentioned. And this influence of external contamination is usually avoided because of the packaging. And the polymer materials also will involved in the corrosion, but mainly as degassing and things like that. I'll show you some examples. And I wrote a book last 2 years back, I think. That is, so if you want to get more information, there is a lot of things in that book. If you can read that. So that's the first part. Then I will go to the second part. Probably we'll have a break now.